Okay, so thanks a lot for all you guys to attend this new event in this webinar. So it is already the fourth event in this webinar series after having the great opportunity to listen to Mura Arkak and then Jacqueline Sherpen and then Dragan Nezic. Now we have today a great opportunity to listen to a lecture given by Anders Rantzer. So Anders is a professor of automatic control at Lund University in Sweden. So I forgot to say that this webinar is organized by three of my colleagues. So it is organized by Andrea Serrani from the TC of IEEE on nonlinear control systems, and organized also by Claudia Calafino and Bayu Vaya Vardana from the IFAC-TC on nonlinear control system. So it is a sister IFAC-TC of the IEEE-TC, let's say. And myself, I'm Christophe Prieur, the TC chair, IFAC-TC chair. So everyone knows the bio of Anders by heart, so probably I don't need to spend too much time, but maybe I can just recall you that he's a professor of automatic control at Lund University in Sweden after getting a PhD in KTH in Stockholm. And then he got a postdoc position at University of Minnesota in the 90s. Okay. And he spent 2 years as visiting professor, first at Caltech and then at University of Minnesota. So Anders got many awards and got a lot of distinctions. In particular, he is a fellow of IEEE. He's a member of 2 Royal Swedish Academies, one Royal Swedish Academy of Engineering Science and a Royal Physiographic Society in Lund. And he was also the chairman of the Swedish Scientific Council for Natural and Engineering Sciences. So today he will present a great lecture about his work on modeling, analysis, and synthesis of control systems. And the title is Nonlinear Optimal Control for Large-Scale Adaptive Systems. And before giving you the floor, Anders, please give me the opportunity to remind to all community the deadline that is approaching. So we have soon a deadline for the NOLCOS. So you know that the NOLCOS will be organized in Australia in early next year. And the submission deadline is very soon. So it is in 10 days from now, let's say. Okay, so do not hesitate so it is still time to write your best paper for this great symposium. So now it's time to come to the lecture of Anders, and now maybe I can stop sharing my screen and give you the floor, Anders, if you are ready to start your lecture.
Okay, thank you very much. It's a real privilege for me to be able to lecture to this audience. I'm really happy about this opportunity, and I hope I will also be able to get some feedback from you. So we agreed that if you have questions, please write them in the chat so that you don't forget them, and then we will bring them up towards the end. So the topic that I will speak about today is actually a double topic, because I've been interested both in scalability and adaptation recently. But as you will see, I view it as connected subjects. So I think it's very natural to speak about them together. The question about how to control large-scale systems, it's quite an urgent one because there are many big infrastructures that are relying on control engineering solutions. And maybe the most obvious one is the energy network. Here's a map of Europe and the power network. And this currently is being under a lot of reconstructions because of integration of renewable energy, which has created many control problems when it comes to matching consumers and producers when you have big variations in access to wind and power, for example. But so it's a a problem that's urgent right now, but it's also a very old problem. Actually, you can go back to 200 years before Christ, and this is a map from Chengdu in China. And already at that time, they were building infrastructure to control the flow in networks. And these were water flows, and because there was a need to use the water for irrigation, but there was also a need to prevent this water from creating flooding problems. So various kind of control techniques was introduced to control the flow. And in general, I would like to consider buffer networks. So it could be large-scale networks where you transport commodities between producers and consumers. It could be water, it could be electrical power, it could be traffic or data. And many of these networks need control, and they also have features in common, even though there are also differences, of course, as well. You need to deal with a discrete and continuous commodities. You need to consider stochastic or deterministic models. And there could be multiple commodities in the same network and human interaction. So there are many sources of complexity, but there are also many opportunities to develop mathematical tools that can really make a difference in this context. So what we will be looking at is scalability, which means that we want methods that can work for really large-scale systems, and both in terms of control design, but also in terms of verification, modeling, and objectives. So this third item about modeling is of particular interest because even if you build models for each of the components in the large network, it's usually very expensive to maintain these models. So if you can do it by automatic updates, that's of great value. And that's why I also will discuss adaptive control methods in this lecture. So let's first look into different approaches to large-scale systems. And I would like to start with an example. I've been interested recently in energy networks, and here is a slide from my Danish colleagues in Aalborg, illustrating how the energy networks of the future will look different from today. So in Sweden, it's quite common to have district heating networks because it turns out that it's much more efficient to burn fuel in a centralized unit than to do it in every house separately. In this way, you can save a lot of energy in the network, and then you distribute heat through a water network. But in the future, there is a big need to also get rid of these fossil fuel units, and the goal in many countries is to entirely shift to an energy network which doesn't rely on fossil fuels anymore, and that will create new demands on how you do the distribution. So typically the district heating will need to use lower temperatures because often the excess heat that is produced comes at lower temperature, and then it's too expensive to heat it up to the levels which are used today. Especially if you use solar panels on the buildings and you maybe want to connect to wind turbines. Maybe you have excess heat from other units that you want to take advantage of. There will be many control problems in this context, both in terms of flow and temperatures. So one example that we see already today is that if we are running a district heating network at in the winter in Sweden, it could very well be that there is not enough energy to give all the customers what they want. You see here that every plot here to the right is the indoor temperature in the buildings, and here in the beginning everything is fine, everybody gets 20 degrees that they are asking for, but when the temperature outdoors go down towards -20, then some of the buildings are seeing a significant drop in temperature, and typically those are the buildings that are further away from production. So by the time that the water reaches the building in the end, it's not it doesn't have enough temperature to heat it up. So the question is how you can make the system more fair. Maybe not, if there is not heat for everyone, it could be accepted that the temperature goes down, but it should be more evenly shared between the buildings. The problem, if you want to solve that, is that there is nobody that knows the entire network entirely. So at the production unit, you don't know really what's going on in the building, and even if you would send temperature measurements from every building to the production node, this node doesn't have the detailed model, so it doesn't know how to make adjustments based on that information. But nevertheless, let's look at what the network looks like. And this is where the nonlinear aspects come into play, because a typical model for one of the pipes is involving quadratic terms. So the pressure difference is proportional to the square of the flow. So you get constraints of this type. The pump is producing a certain pressure difference, and this pressure will drive the flow of the water through the network. But you get these quadratic terms, which brings this into a nonlinear problem. It's a nonlinear problem, but it's generally a convex problem. So the convex, you can use these constraints in an optimization problem, which is solvable. But as I said before, the model is typically not available in one place. So that's the other issue we have to deal with. So the way we decided to approach this problem was to have a centralized optimization where you take these constraints, the quadratic inequalities, into account. But what we need to collect from the buildings is their demand for the flow. So in every building there is a controller that computes what heat flow they want, and then this should be sent to a central coordinator, which is then trying to minimize the deviation between the desired flow and the actual flow that is sent to this building. And then you collect all this in a vector queue, and you solve a convex optimization problem like this. And then out in every building, there is a controller to deliver the Q hat. And in this way, it's not a perfect solution, but you can see that the differences compared to the without coordination is significant, and most likely the buildings wouldn't even notice that there's a shortage in these networks. And the difference from what you could get with a centralized model knowing everything is not so big in practice. So this is an example, and I use this as an introduction before I now step more into the mathematical aspects of large-scale control. So remember that I was interested in these buffers where commodities were moving back and forth. So if I use a first order model for the dynamics in each node, you could think of a commodity which is has a time constant, maybe because if you have hot water in one place, it will not stay hot forever. So there's a time constant corresponding to the temperature or heat losses. Or if you have a water network, you could have some leakage of water in the irrigation network, which corresponds to this time constant given by the parameter A. But then you have the possibility to move things around in the network between different buffers, and this is modeled by these input terms. So Uij is what goes from node J to node I, and Uji is the opposite direction. And then disturbances. So the question in presence of disturbances, you can ask, how should I use the input that I have available to minimize the effect and the errors in the levels at the different nodes of the network. So this can be stated as an H-infinity optimization problem and solved using standard techniques. But usually that would give you a control law where every controller needs to know the state in every other part of the network. So it will be a full matrix K, and for a very large network, it would be very impractical. But it turns out that this H-infinity optimization problem doesn't have a unique solution. In fact, there is an optimal controller which is extremely simple, and you don't have to compute the solution to a Riccati equation. You can just take the parameters in the local nodes and feed them into a control law like this. So this was a big surprise for us when this was discovered some 5-6 years ago. And since then, we have been trying to understand the reason for this and how it can be used in more general settings. So this is the theorem that explains, or at least generalizes what we saw on the previous slide. If you study a linear system where the A matrix is symmetric and also stable, then you can use a simplified expression to get an optimal controller. And you actually don't need to solve a Riccati equation. So this was all for linear models. So now in this seminar, it's natural to also look at what can we do for nonlinear system. And there's a simple modification here that allows you to make a nonlinear dependence on the state in the B matrix. In that case, almost nothing changes. We just put in an X in the expression for the B for the controller, and when we want to compute what the minimal value of the norm, we also have to do in maximization over X. And how should we explain why this works? It turns out that this A matrix, which is symmetric and stable, can be used to create a potential function, if you like, or a cost function, which doesn't solve the Hamilton-Jacobi-Bellman equation, but it solves the corresponding inequality. And this is all you need to get an input-output relationship of the kind that we need. So this particular case was published last year at CDC, but in this year we also have other updates to other kinds of nonlinear settings where this idea still works out. So that was H-infinity control, but I would also like to mention another approach to do control for large networks, which is using the old idea of inverse optimal control. So the optimal control problems are that we consider are this type. It's continuous time, it's nonlinear models, and it's a cost function. In this case, we have a quadratic dependence on the input, which gives us analytic expressions for some of the computations. But notice the word inverse. Actually, we're not going to start with the optimal control problem and solve it. We know that can be very hard for nonlinear problems because it would lead us to Hamilton-Jacobi-Bellman type equations, partial differential equations, which could be very difficult to solve in general. But we will use instead the idea of going in the other direction. So this goes back to Kalman, who was already looking at linear controller and asked which of the linear controllers are optimal for some cost function. And this has been studied by many people since then, but I think it hasn't been used before for the purpose we are looking at here, namely how to construct and tune controllers for very large-scale systems. So notice the statement here. If I have a function v with which set and a controller to satisfy a certain inequality, then I can construct an optimal control problem for which this control law is the solution. And essentially what you need when you start, if you want to use this idea, is a control Lyapunov function. That is a V which works as a certificate for stability for some choice of control law. So it doesn't have to be this kind of control law originally, but then if you have such a control law, you can replace it by the control law given by this expression, and it will still remain a stabilizing controller, provided that you had a control Lyapunov function to start with. But what's really the point over here is the way we are going to use this in the end, namely for controller tuning. So recall that for many applications, there isn't an obvious criterion what you should optimize. Usually there are many different criteria. One could be that the control law should take away disturbances quickly, but another one could be that you shouldn't have too aggressive control. You shouldn't have too big control signals. So it's quite often that when you construct a cost function like this, there is a trade-off. Either we put the emphasis here to make the control action less aggressive, or we put the emphasis on this term, which is giving us faster error decay. So the size of this R matrix, which is the weight, could be important in the controller design, because by increasing the penalty on some of the inputs, that will result in a solution for which those inputs are smaller. And so here we see that if we have solved this problem once, so we have a control Lyapunov function and a corresponding control law, then we can start to play with the R matrix, because if we have one solution, we can get others. And we don't touch the V. The V is still the same all the time, but by playing with the R matrix, we can change the controller, and we will change the trajectories of the system. V will always need to be a Lyapunov function, but we will have this very simple tuning knob, the R matrix, which allows us to make the trade-off between disturbance rejection and control activity. And if the original V function was sparse in the sense that the gradients of V versus this Jacobian matrix has lots of zeros in it, then that will give us simplified expressions for the controller, so we can get localized controller that don't need measurements from all of the network. So sparsity in G and V will give us sparse controllers that are scalable and useful for large-scale systems. And I just want to give you a simple example where this could be used, and that's in phase synchronization. It's a well-studied problem in the literature. These kind of Kuramoto models are well known when it comes to synchronization. But here you see that these R matrix, if you put it as a diagonal matrix, it just comes in as a number of parameters. And you can choose, once you have once you know that this is a synchronizing dynamics for some values of R, you can play with the R and you will still have synchronization. And in fact, you will have an optimal cost function where where the choice of R will determine the trade-off between the control activity and the speed of synchronization. So you can speed up the synchronization in some parts of the network and keep it unchanged in other parts, for example. So these were three different examples where nonlinear control plays a role in large-scale networks, and I think there is much more to do in this area. And but rather than going into more examples, I will now move into the second aspect, maybe the modeling. And in this context, I will mainly use linear systems, but the control will still be nonlinear because of the adaptations. So let's go for the problem formulation. Of course, adaptive control has been used for several decades, at least from the 1950s, where it was introduced in the context of aerospace industry. And now if you make a search in Google Scholar for adaptive control, you get almost 5 million hits. So it's really an area which has been seeing a lot of research over the years. And in particular, in the adaptive control literature, people have been focusing on stability of the closed loop and asymptotically optimal performance. Usually there was less focus on the performance during the transient, and we will come back to this. But another thing you find in this literature is that many natural ideas and suggestions for theorems turned out to be false, and people were able to construct counterexamples to those conjectures. So now this area has received a lot of renewed attention because of the progress in machine learning. So there's a lot of efforts now to try to merge theory for machine learning with control theory. And in the machine learning literature, there has been much more focus on the transients during the learning phase, and the concept of regret bounds were introduced to measure such transient performance. So I think it's interesting to go back to some of the questions that were studied in adaptive control literature, but see what we can do in terms of quantifying the performance during the transient. And a disadvantage with many of the current approaches based on learning theories, that you have to have a stabilizing linear controller when you start, or at least a stabilizing controller that allows you to do experiments. So if you have an unstable system, it's very hard to apply most of these methods from learning theory. Another aspect is that is the treatment of unmodeled dynamics. We are used to in control to saying that we can use simplified models, and unmodeled dynamics can often be taken care of by the feedback loop, but this is something you have to be careful about in the and which could be hard to deal with in a theoretical setting. Anyway, so I will be looking at what's called minimax adaptive control. It was introduced already in the 1990s. And I will tell you a little bit about what has been going on since then. And my own work and interest is quite recent. So much of the work in machine learning is done in a stochastic setting. So it's natural to ask, should we work with stochastic models or deterministic ones? I find that stochastic models are quite hard if you want to have a rigorous result, because usually you need nonlinear feedback, and that creates very complicated probability distributions in the end. So for this reason, and also for the reason that I want to be able to deal with unmodeled dynamics, I've been looking instead of at deterministic approaches and worst case disturbances. So this is, of course, not a new idea. We had this discussion already in control theory in the 1980s. Should we go for LQG, or should we shift to H infinity? And there were strong arguments for the H infinity type methods because of their ability to deal with unmodeled dynamics. And maybe this discussion, which was going on in the 70s and 80s, could now be making contributions to the ongoing discussions in machine learning about adversarial disturbances and adversarial learning. So the setup that I've been looking at is systems which have linear dynamics but parametric uncertainty. It could be quite significant parametric uncertainty, so that no linear controller can even stabilize all the system under all possibilities for these linear dynamics. And if you are in such a situation, you really need a nonlinear controller, but an adaptive controller can potentially do the work by first estimating those parameters and then exploiting them for control. But then we want to do that in such a way that even during the learning phase, the map from disturbances to errors is not too big. So we want to bound the gain in this direction for the closed loop system, including the adaptation. So just some word of caution. There was a study done already in 2004 by Alexander Megretsky on a very simple problem. So here is a first order linear system with just one uncertain parameter. But the thing is that if this parameter is not known, the system could be unstable, and it could be even possible to stabilize it with a single linear controller, because clearly if you want to bring in a linear controller, you should compensate for large numbers of these parameter A. If A is very big, you need a negative feedback here, and if A is very small, you need a positive one. And if you don't know the value, there is no linear controller that will stabilize the system for you. But what Megretsky proved that this size of uncertainty in the A parameter will be mapped into a lower bound on what is achievable in terms of gain from disturbance to errors. So actually the size of the best possible gain grows linearly with the size of the interval. And in particular, this means that if you don't put any bounds a priori on the parameter A, you will not be able to find a controller that achieves finite gains from disturbance to error. So that's a simple conclusion. Don't even try this problem unless you are willing to put an a priori bound on the size of the parameter. So this is what we will do. We will study the case when you have n different possible linear models. So it's a finite number of models. One of them must be true, and but we don't know which one is true. And this could mean that they could all be unstable and so different that there is no linear controller that will stabilize all of them. But still, we will see that it's possible to construct a nonlinear controller which stabilizes the system for all possibilities of the AB matrices. So this is our problem formulation. Find a controller that keeps the L2 gain from disturbance to error below a given bound for all the models that we are considering. Okay, so now we will show how to solve this problem using dynamic programming. So using dynamic programming for robust control problems is not a new idea. In the problem I'm considering, in the case that there is a known model, the problem to minimize the gain from disturbance error is an H-infinity control problem. And it was solved using Riccati equations in the famous 4-author paper. It was solved using linear matrix inequalities soon after. And the particular approach we will take was introduced by Bassar and Bernard in their book on dynamic games for H-infinity control. So dynamic games will means that you are having, in this case, two players. So one that is trying to minimize and the other one is trying to maximize. And you have a dynamical system governing the evolution of X. Here we want a control law that decides the input based on measurements of X, but subject to disturbances W, which are trying to maximize. So there is a number of famous names. Maybe Isaacs is the way in the name you most often hear in terms of in context of dynamic games, because the Isaacs equation is the generalization of the Hamiltonian-Jacobi-Bellman equation to the game setting. But actually, there was a Swedish author at the same time, Zachrisson, who also published the same equation in parallel to Isaacs. So let's see what the Isaacs equation or Zachrisson equation gives us in the context of a linear system with non-A and B matrices. This is the work of Bassar and Bernard. They noticed that you can write down, you can turn this min-max problem into a Riccati equation. So here you are having a cost function P, which is not known in advance, but you can solve for it. And what you see here to the right is the step cost. That's the same cost as we have in the objective. But after one step, you also look at the future cost, which is given by this term. And then the two players are doing their work in terms of minimization and maximization. So if if gamma is big enough, that means that the gain from W to X and U can be made smaller than gamma. This means that the Riccati equation must have a solution in terms of a positive definite matrix P. So now we're going to extend this to a setting where the A-B pair is not known. So that's the adaptive problem. In this case, the disturbance player, the maximizing player, is allowed to pick not only the disturbances W, but also the model in the end. So when I decide the control of mu, I have to take all the possibilities for the model into account. And this still is a setting where gamma quantifies the gain from disturbance to errors, and therefore also gives me a robustness to unmodeled dynamics. But unlike the work of Bazar and Bernard, which gave me a linear state feedback controller, it turns out that now I will not be able to use a linear controller for the same reason we said before. You really need to learn the values of A and B, otherwise you will not be able to control the system. So there was some early work on this by Deninsky and Bazar during the 1990s, but now we are going a little bit further. And the first theorem is to prove that the optimal controller still can take a state feedback form, but you need an extended state. So instead of just X, which is the X that we see in the state equation originally, we also have this Z matrix, which collects all the relevant information in the historical data that are needed to estimate the matrices A and B. So this matrix is the same matrix that is sometimes called statistical sample covariance, is used in system identification to estimate models from data. So it shouldn't come as a surprise, but actually the striking feature here is that we can prove rigorously that no other parts of the historical data needs to be kept in the memory in order to control optimally. This is all you need to know about the history and in order to control. And this was published in the conference L4DC. It's called Learning for Decision and Control, and that's an annual conference which is coming up now next week in Stanford for this year. So the reason why we could make that conclusion is that we can actually rewrite the entire game problem in a different way. And here you see that instead of just before I had a penalty on X and U squared and minus gamma times the disturbance W, I now have something that looks quite different. So this should be compared to this expression. I previously had minus gamma squared W squared. But it turns out that this W can be solved for in this equation. And then you see that if you substitute the difference between the other terms into this cost function, then the past contributions to the sum can all be summarized in terms of this matrix Z, which kept the relevant aspect of history in the memory. And this is what we see over here. That's the notation for multiplying this matrix from left and right with the A and B matrices and then taking the trace. So by rewriting the dynamic game on this form, we now have a set of dynamics which is no longer having A and B in them. So now the dynamics is known, only the cost function, the last term of the cost function has changed. And this brings the system into a form where we can apply the standard Isaac's equation. So I also have another theorem, which is helping me to solve these problems in practice. And it turns out that the Bellman or the Isaac's equation can be solved using matrix inequalities of this type. And once you have found matrices K and P, which solves these inequalities, you can turn this into control law. It's not a linear control law because it's actually a switching control law. But you switch between K depending on which model fits the past data best. So it's a very simple certainty equivalence control law. You collect your historical data, you check which model fits best. That determines the I, and that determines also which of the controllers you should use. So for the details, you would have to look at the L4DC paper, but I think the intuition is clear. There are a few things that could be noted here, that if you put in all the indices the same here, then the last expression here will actually go away because AI minus AJ will disappear, and the other term will also disappear. And then what remains here will only be the Riccati inequality or the Riccati equation. It's an inequality that corresponds to the Riccati equation. So for the case that you have a single model, this will be this inequality will be the same as we have for solution of the standard H infinity problem. If you have several models, then you get more conditions, and you can interpret these matrices in very natural ways. But to solve all the inequalities, it's a non-trivial matter, but there are approaches that can be used and which work. There is also an interesting aspect that you see here, that this last term has a minus sign in front of it. So if we could make the last term big, that helps to solve the inequality. And this is sometimes called the excitation. So in adaptive control, there is a trade-off between excitation and exploration, and it's well known that you have to activate your input sometimes to learn the value of the unknown matrices, and this is explained by this last term. So I want to show you before I end an example. I just have a double integrator, so it's very simple dynamics, but I have uncertainty here of ±1. So when I do control, I don't know whether it will act in one direction or the other. So it's an unstable system with an unknown gain. And for these systems, there is no linear controller that can do the job. No linear controller can even stabilize the system if the sign of the input gain is not known. But with an adaptive controller, you can do it, and we can use the matrix inequality we had on the previous slide to do it. So here we have expanded it to a third order model. It maybe looks a bit unnatural to have a third order model when it was only a double integrator, but this is because we couldn't measure all the states. So we write a third order model in terms of the input and output values. And now this is a state which is also measurable because we know all the inputs and the outputs. So now we can apply the previous theorem with a set of models which includes both A and B and A minus B. And we solve the inequalities, and we get some matrices and the controller that does exactly what it should do, namely first estimate the uncertain sign and then use the estimation to control the system. You see here that there is a transient in the beginning, but because of the gain bound, the transient cannot be too big. Here, what you see down here is that I have actually not kept the gain constant, but after some time I switched from 1 to -1, and obviously then the controller got confused because it had already determined the correct sign, and then suddenly the sign switched. And you see that here I got a transient which is even bigger than I had in the beginning, but this is because I had already collected data for a while. So I had data consistent with one sign of the parameter, and so the controller was very confident that it was already doing the right thing. So when I changed then the value of B, it took a while to learn that the value had changed, but it works still. So I guess my hour is running out. So I would just like to say that I find it very interesting to look at these large-scale problems and see how we can deal with them with controllers that are sparse, so they can be implemented even for very large systems. And interestingly, it's possible to sometimes get sparse controllers without sacrificing optimality if you state the optimal control problem in the right way. We also saw that inverse optimal control could be used for tuning of dynamics. You have without solving complex partial differential equations. We also saw that in the context of adaptive control, extending the state with a sample covariance matrix can be useful to get an optimal controller even for those problems. And we saw that with Riccati type of inequalities, we can get bounds on the L2 gain, even for the nonlinear loops that involve the adaptation. So there are many natural generalizations. There's a lot of things still to study for these problems. I want to acknowledge the support from some funding and also from a number of PhD students and postdocs that have been working on related problems in the past few years. So thank you very much for your attention.
Thank you.
I see that there are a few questions in the chat.
Yes.
So should we address them now?
Yes.
Okay, so first one. Some buildings might not get the desired heat being far from production. Then why not to incorporate multiple production units? Yes, that could be a solution, definitely, but it's costly to build new production units. So if you could do it with a simple coordination, I think that's a much simpler way. Do you want to comment more on that?
I don't know. So, Sai, do you want to open your micro? No? Or are you satisfied with you?
Yeah, Christopher. Yeah, I got the thing, but just there was a confusion that since in district heating, there are many sources, production units coming into play. So whether this distance will still matter or not, this was a dichotomy in my mind, but I think future advancement will show. But since you can always put a production unit near the building that is at far end, it may be some smaller unit, maybe a solar panel or something like this, then that may eradicate this problem. But
yeah, it's a possibility.
Yeah.
I agree. Sometimes this could be a feasible solution, but not always.
Yeah, agreed. Thank you.
Thank you. So let me move on here. Dong Yun Bu is asking, normally when using HJB inequality, we get suboptimal L2 solution. So when we are looking for L2 gain, what we are really, what we are really looking for is minimizing the gamma. Remember, this gamma was a parameter in the game formulation. So optimality in this context means that we are able to solve using as small gamma as possible. And it turns out that if you look at the smallest possible value of gamma, you could either solve with equality or you could solve with inequality. But both types of solutions are certificates that this gamma is achievable. So an inequality sometimes allow for more possible solutions, and this can give me these sparse solutions that I'm looking for. It's quite well known for in H-infinity. There's another way to view it. An H-infinity norm can be evaluated for linear systems in a border plot. So you just look at the frequency where you have the highest peak of the border plot. And what an H-infinity control is to push down this peak value as much as possible. But what's going on at other frequencies doesn't matter because they are not contributing to the peak. And then you can play with controllers. Some controllers could be sparse and scalable. Maybe they have higher gain outside the peak frequency, but that doesn't matter because the H-infinity norm is still the same. So this non-uniqueness can be exploited, and that's I don't know if I answered your question, but at least I tried now.
Okay, thank you very much.
Okay.
The next two questions are coupled, so you can maybe answer to both.
Okay, inverse optimal control. Do you have any restrictions on functions Q, F, and G? Usually the dynamics I'm having is fixed, but what I'm playing with is the Q. In those slides, maybe we can go back. So the slide was here. Obviously, if R is being, if I make R smaller to put less emphasis on the controller, what will happen with the Q is that it will become bigger. Because Q is the expression on the right-hand side. So that's why this still works as a trade-off. I make R smaller and Q becomes bigger, and that means that the interesting trade-off between control activity and disturbance reduction can be investigated in this way. But the F and G are usually fixed because they are determined by the plant.
Thanks, Anders. Thanks.
Okay, so it was the same question for the next. Omar asked the same question.
Okay, so let's go on then.
Next one is a question of Hafiz, sorry. For inverse optimal control.
Yes.
What do you say about other controllers form like Zontax formula, and through inverse optimal control being optimal gives excellent robustness, but does it usually result in quite complicated control laws or not? Okay, the question is quite vague. Huh?
Yeah, it depends on.
Depends.
You have to be if you have a controller which is stabilizing. But as long as you have a accompanying cost function V, you can look at this expression and then see if this controller is an option. But obviously, if you want to use this theorem, you actually need a controller of this form. But this is a consequence of the fact that I put a quadratic penalty on U. if you are playing with other penalty on you, like a cubic or something like that, then you will get a different expression for the controller.
Okay. And I think the next one is about min-max dynamic games. I'm not sure, but
yeah, is it this one?
Assuming that one might extend the idea of consideration of the worst case disturbance in the deterministic setup to a nonlinear system, is there some way we can define what is the worst case?
Yes. So if you look at the game theory literature, like this one, there is if you solve the Riccati equation, that gives you a linear controller for the input, but it also gives you a linear controller to generate the worst disturbance. And this you can do also in the setting for nonlinear controllers. So it's interesting to also look at expressions for the worst disturbance, and it's also interesting to look at what does the worst disturbance do. In general, it wants to keep you confused, so you never really are sure about what is the right value of A and B. So when I did the simulations here, I was running this with without a disturbance. Obviously, if I would run it with a white noise disturbance, it would never settle to 0. But if I would do it for the worst possible disturbance, it would go to 0. But my estimate of the correct value of the sign would never really converge. I would still have some uncertainty about what the correct value is. But this is only what I saw in some examples, and I haven't proven any theorem about it.
Okay, thanks. Thanks for this very inspiring discussion. And so thanks a lot for your lecture. So you can see that the next section has been part of the discussion between Bowani and Michelangelo Bean. So it was an interesting discussion about hybrid systems and the fact that you are mixing continuous and discrete dynamics, you see, with your min controller. Okay. So I don't know if Bowani, do you want to come back to this question, or are you satisfied with the answer given by Michelangelo Bean? I don't know. Okay, anyway, we can read the question. How can I select? So it was related to the slide where we have the mean, remember? You select the best model amongst all possible models. It was a slide where we have a
yes, the expression for
mean.
the So
yeah,
here.
exactly. Yeah, this one. Yeah. Nice
okay.
slide.
Which question was it now?
How can we select the model set AIBI? And
how do we do that?
Uncertainty usually continuous, but should the set be? Is it possible to have also the set as many elements as possible, or is it also possible to consider discrete dynamics? Or I don't know precisely what Bowani wanted to ask. Yes.
Yeah, so I'm not sure if I got the question.
Me neither.
If you have a small number of models, you can simply run through them all and check this expression for each one of them. If you have a very big number of models, it could be very costly to do this, to run the controller like this. And I haven't really studied how to do it more efficiently.
Okay, I see. Thanks. It is a very interesting expression. It looks like the argmin controller, you know, given by I don't know, a long time ago by on switching systems where we select the best controller amongst different controllers. So,
but notice that this theorem is only a sufficient condition. So if I'm able to solve the inequalities, then this controller has a bounded value of the input-output gain. But
Yeah.
I'm still optimistic that we will be able to solve for necessary and sufficient conditions. So that's a big challenge, but
yeah, maybe there are some connection. Yeah, I remember the work of Patricio Colaneri and José Jérôme quite long time ago.
yes, absolutely.
Yeah. So
yes.
it is a quite similar expression, but not in terms of the error of the in the dynamics, but in terms of the Lyapunov function value. So
Yes.
this is very interesting. Nice to see this expression. And the next question is a question of Emilia, given by Emilia. So first, she wanted to congratulate you for your great talk, and maybe Emilia, you can open your micro to ask you to ask.
She's asking, can I guarantee internal stability?
Yes.
Yes, because it has to be internally stable because it's the map from disturbance to input and state, and so the state cannot there cannot be any parts of the state that that go in that are not visible and not included in the stability analysis.
Okay, thanks.
Thank you, Anders. Just in the continuous time, probably you know there is a northbound problem when you have unknown control direction. And there is another approach, of course, but it was interesting to see the same in a discrete time with the other approach.
Yes, I agree that the continuous time version of this would also be very interesting to look at. Obviously, adaptive control theory has been considering both continuous and discrete time, and it should be done also in the context of minimax.
Mm-hmm. Thank you.
Okay. Is there any other question? No? So I do have a last question. So I'm sorry if time is running, and I see that it is already quite late here in France. But so can you, anyway, if you have 1 minute to answer to this question, can you generalize your approach on when you to dynamic control? I mean, about the slide. Yeah. About the slide.
So obviously, if you cannot measure the full state, you would need an observer. And
exactly, I want to use an observer. Yeah, exactly.
Yeah, so in this double integrate, I suggested using an extended state like this, but even this one is assuming that I have exact measurements of the outputs, and if the outputs come with measurement error, the use of an observer would be very natural. And we did some preliminary work in this direction by looking at minimax state estimation, but it's the first steps. It's actually it was published a paper on minimax state estimation with my student in ACC last week.
Okay.
But it turns out that in that case we don't have a counterpart to this theorem because we cannot compress history into one matrix which is collecting all relevant information and independent of the models, because when you have outputs instead, how you should filter the outputs depends on what assumptions you are making on the dynamics. So it's still not a fully complete solution, I would say.
Okay. I will look on your next paper on that. Okay, so let me thanks again, Anders, for the great talk. So thanks a lot. And I don't know if there are any other question or it's okay. So maybe we can close the presentation. So
Thank you for coming.
yeah, thanks to everyone for coming, and please stay tuned for the next lecture.
And please, you are all welcome also to send me emails if you want to follow up later. Thank you very much.
Okay, thanks. Thanks a lot.
Thank you.
Okay, Anders.
Thank
Bye-bye.
you. Thank you.
Thank you.
Bye.
Bye.
Nice to see you all.